Your internet is down, but you're not unhappy, thanks to the Dino game. It's a cute and funny game. Hey, did you notice that? That plant looks carnivorous. Nothing like a falling meteorite to make the game more exciting. Wow, we have food lying around too, but which part of the multiverse has this kind of Dino game? Well, you are watching a clone of the Dino game made in Python. By the end of this video, you will learn how to write this simple game from scratch and customize it however you like it. This is an introduction to basic game programming in Python. You don't necessarily need to know Python to understand it. First, let's go into a clean empty directory. As you can see, there's nothing in this directory. I'm going to create a virtual environment called game env. This is my preferred way of creating a virtual environment. You might have a different method. Give it a few seconds so that all the required files for the virtual environment is created. Next, let's go and activate this virtual environment. So go inside game env, bin folder. There should be a script called activate for your shell. In my case, I'm using the fish shell, so I can use fish. If you're using bash or C shell, you can use a different one. Or if you're on Windows, you could use a batch file here. So now I'm inside the environment. Next, let me update pip. Updating pip is always a good practice. You might have an older version installed, so it just takes a few seconds and it gets installed. Next, let's install Arcade itself. Arcade has a number of dependencies, so it might take some time. So wait for it, and it's done. Next, let's create a simple empty file called main.py. So there you have it. I have an empty main.py, which I shall open in my editor. So let me start off by importing Arcade. Importing Arcade is probably the only import you need because everything would be inside the Arcade namespace. Now let's define a couple of constants. The first constant I would like to define is the screen width. In this case, it's 800 because that's a wide display. In case you want to make it wider, you could do that, but I thought 800 is a fairly reasonable resolution that most people would have. The height is not so much. The height is, if you remember the Dino game, just 150 because you have to make it fit the error message part of the browser, and the window title itself, which might not be visible in some operating systems if you don't have the borders, but it's always nice to define. And finally, the background color is a gray color, 247 on red, green, and blue, which will give you the typical gray background that you would expect for the Dino game. Next, let's define a class which is derived from arcade.window. This is a standard class that is required in most arcade programs. I'm calling it Dino game. This is the constructor of this class. I'm just passing the width, height, and title. This is useful in case you want to keep changing it. As you would notice in line number 13, I'm turning off the mouse cursor because I feel mouse cursor is not required in this game, so it would be a distraction. So I'm just turning the mouse cursor off. But if you move your mouse cursor outside this window, you would be able to see it again. It's just that when it moves towards you inside your game window, it would not be visible. On line 14, I am setting the background color to whatever background color is defined as the constant here, so that every time I draw, I don't have to set the background color or paint the background color. Arcade automatically sets, once you set the background color, Arcade automatically knows what to do. Next, I'm defining a method called onDraw. onDraw is a required method when it comes to creating a window. All I'm doing here inside onDraw is to call arcade.startRender. StartRender is just to set up all the drawing required for Arcade. In fact, it gives an opportunity for Arcade to do some basic painting like the background color that we just set in line 14. And this is our main function. Our main function just creates an instance of this arcade.window derived class called Dino game. As you would notice, I'm not passing this window or saving this window into a variable. At this point, it's not required because even if I did, that variable would be unused. But very soon we would require this variable and save it somewhere. And Arcade requires some sort of a loop to run itself. So in line 22, I call arcade.run. Always choose this to be the last part of your main function because this part does not return until you close the Arcade window. So this is sort of like a loop which keeps on running throughout the game, and it'll only exit or come out to the next line once that game is closed. And finally, we are calling the main function, and this is it. This is pretty much a skeleton of what we need to do here. So let's save that. Let's call this using Python main.py. Let's see what happens. As you can see, it's just a blank window, but it shows a window without any errors. So our first step is successful. Okay, let me try to explain how the coordinate system of Python Arcade works. In Arcade, we use what is called the first quadrant in mathematics. That is, the X and Y coordinates are on the bottom left of the screen. X coordinate increases from left to right, as you can see here, and Y coordinate increases from bottom to top. Our screen window is going to be 800 pixels wide and 150 pixels high. So it's a narrow, or you can say that it's a wide but short looking window, and the top right coordinate would be X coordinate 800 comma 100 and Y coordinate 150, to give you an example of how I would position things in this window. Now, how would I draw things? I would probably draw things by mentioning these coordinates, and if I wanted to position a dinosaur image, now I would probably use the word sprite, dinosaur sprite. In many cases, a sprite is similar to an image, but it's cut up or a part of an image. But in video game terminology, sprite is more commonly used. So in most part of this video, I would be using the term sprite and image interchangeably, but think of sprite as a moving image that is displayed on a video game screen. Now you would notice that in the case of showing this sprite or positioning the sprite, I have used a plus in the middle of the sprite. Why is this in the middle? Because Python Arcade provides attributes for setting the center X and center Y of a sprite. So it's quite easy for me to position it exactly if I just mention the center X and center Y. For example, here I might be positioning it, the center X, somewhere along 50, and it should appear here. And if I increase the center X, you should get the illusion of animating this dinosaur as it is moving to the right. Okay, that was a quick overview of how to understand the coordinate system in Python Arcade. Why am I using the Python Arcade library? Why not Pygame? Pygame is a port of a C library called SDL. In my humble opinion, it is not very Pythonic. Python Arcade, on the other hand, a relatively new library is native to Python, hence uses proper Python idioms. Python Arcade is very well documented thanks to its excellent website. It is very actively developed and maintained. Okay, for the next version of this file, I'm just going to show you the diffs and take you through that. Before that, let me show you this interface where you have the old code on the left hand side and the new code, or the code which I'm trying to explain to you, on the right hand side. And there will be a separate window here at the bottom which you can ignore. Whatever you see on red has been deleted and whatever you see on green has been added. So in this case, all you have to do is delete line number 2 and add line number 2 on the right hand side, which imports path library and the GL nearest. So that was just a quick explanation of the interface that you see on the screen. The first addition you have to make are these two lines, pathlib and GL nearest. So pathlib is needed for importing assets that we have just created, and GL nearest is needed for creating that pixelated look, without which it would not look proper. So I'll tell you in a minute what that means. We need to define a few more constants. The first constant I'm defining here is assets path. To explain to you this, it's basically a way of saying sys.path and omitting a fairly number of functions that is required to wrangle paths. Path manipulation has become quite easier in recent versions of Python. So I'm going to use pathlib.path file to identify what is the path to this main.py. And once you reach that main.py, I'm just going to go to the parent directory and go into assets. So what this entire line does is it looks at the assets directory, which is sitting alongside or right next to main.py. Now, once you get that path, you can use it to load other files like textures and images. The ground width is needed to define where the dinosaur needs to stand. So that is 600 pixels in terms of the width. I'm sorry, this is kind of the width rather than the height. So this is just to define a tile of ground. And we are going to use many of these tiles right side by side so that you can create an illusion that the ground is one continuous surface. Level width pixels. Level width pixels is a way of calculating how long one level would be. So it's usually multiples of ground width. So I'm just saying that 4 screenfuls of ground width needs to be used, or 4 times 600, that is 2400 pixels needs to be used for level width. This needs to be a fairly longer or wider than your actual screen width, which was as you can see over here 800. So that's our level width pixels. The last constant we are defining here is called all textures, which is nothing but a list which contains the names of the image files that we need to load. In this particular case, we just need to load Dino run 1 and Dino run 2. Next, we are going to add a new method called setup. Setup is defined right above draw. So you can see that there's a space left here. Setup is needed to set up all your textures. So I'm going to use this to load texture. So arcade.load texture, go to the asset path and define what was mentioned in our all textures constant and load them one by one with the name of that particular texture. So this is nothing but a dictionary, a lookup table you could say, which has, if you pass it the name of that particular texture or image that you want to load, it will return to you the actual object itself. So arcade.load texture is actually doing all the heavy lifting here. Next, I'm going to call self arcade.scene to create a scene object and assign it to the self.scene. Scene, if you remember, is going to be the topmost object here. And if you draw the scene, all the objects inside the scene would be drawn recursively. So it will go inside and draw each of them. Next, I'm going to set up a player sprite. A player sprite is created by just calling arcade.sprite without any parameters. It's going to have a center in 200 pixels and center Y in 444 pixels. This is picked up from an image editor of opening your typical dinosaur sprite. It's necessary for me to define the center because this is how I'm moving sprites. In case I have a sprite, I can either use the corner, the top left corner, to move the sprite, or I can define where the center of the sprite should be. So here I'm defining it to be somewhere off left to the center of the screen, so that I'm just having the dinosaur in the right starting position. Next, I'm going to define the texture, which is basically what image should be displayed, and it is the first frame of the dinosaur run. Next, I'm going to create what is called a player list. The player list is a list of sprites, so it's defined as a sprite list. In most cases, a player list would consist of just the player, but a player could be having multiple other players as well. In this example, I'm just going to use one sprite inside this list, so I'm just going to append that here. And finally, I'm going to add it to the scene. So the scene contains the player sprite list. Next, I'm going to add a line to onDraw, which is to draw the scene. So when you're drawing the scene, I have to remember to add this filter equal to GL nearest. Otherwise, it'll have some artifacts. These artifacts look like streaks or lines on the dinosaur, which you want to avoid. So if you don't pass filter equal to GL nearest, it might have those artifacts. And this is how you can remove that by using what is called a nearest algorithm, so that whenever the image needs to be shown in a scale different from what its original scale is, it will not have the scaling artifacts. Instead, it will use a very blocky algorithm or a pixelated algorithm. And like I said earlier, we did not assign the arcade window derived Dino game instance into any variable, but here we are going to call setup. So I'm going to assign it to a variable and call setup. And setup we just defined earlier up. So that will take care of creating all the initial objects, in our case creating the player sprite, and when you call arcade.run, that player sprite will work. So let's run this code and see what happens. And there you have it, a proper dinosaur being displayed. Next, we will try to animate this dinosaur by using 2 frames of the dinosaur being running. So for that to happen, we need to have some notion of how much time has passed. So this is not in terms of number of seconds, but if you look at setup, you will notice that I'm setting up a variable called self.elapsed_time to a floating point 0.0, and that will help us keep track of the moving time. So this might not be seconds, this might be maybe 1/60th of a second, or whatever the frame rate might be. The next change happens after the setup function. After setup, I'm going to add a new method called onUpdate. OnUpdate is a special Python arcade function. It's called every few times or maybe several times in a second. Typically in video games, if you want to get an illusion of an animation, you would need to do it maybe 30 frames a second or 60 times a second. Whatever it is, it gets passed a variable called or a parameter called delta time. Delta time is something that I would add to elapsed time. So roughly you can say that elapsed time gives me an idea of maybe how many seconds has passed. Next, let me go to offset. Offset is to understand how far the dinosaur has come. In the case of the Dino game, the offset and elapsed time are practically proportional to each other. So the dinosaur is running at a constant speed. The dinosaur might be jumping up and down. It might be making leaps, but it's always moving in the same direction at the constant speed. So the offset, which is the distance covered by the dinosaur, is almost the same. So you can see that I'm multiplying elapsed time by 10. So if 10 seconds has passed, offset would be something like 100. Next, I'm going to set what is the frame of the dinosaur. Like I said, the running of the dinosaur is a two-step animation. There are only 2 frames which needs to keep changing, so that I'm just trying to do a division and remainder by 2. So it will just give me an answer of 0 or 1, and I'm adding that to 1 so that I get a frame of either 1 or 2. Then I'm just calling player list update. This is going to update all the positions inside the player list. You could say that line 47 is a bit redundant at this point, but once we assign a speed to the dinosaur, this becomes important. And finally, the most important step, which is line 48, where the player texture is changed. Now, player texture is nothing but what image is shown by that particular sprite, the active image shown by that particular sprite. As you can see, I'm using string interpolation here, f dino run. I'm just going to make it a little bit smaller to show that it's one single line over here. So the self.texture is actually our dictionary containing all the textures. If you remember, we loaded it up, and I'm just going to say dino -run -dino frame, which could be 1 or 2. And with this setup, let's see what would be the animation looking like. So there you have it. The dinosaur is not moving, but the animation is happening. Next, we'll see how to make the background move as well. Next, I'm going to introduce the concept of moving the dinosaur by moving the camera and possibly showing the score as well. One thing you would notice in the Dino game, amazingly, is that the dinosaur is actually not moving. The dinosaur is kind of fixed at the spot, and the background is moving. And the background is moving in the opposite direction. That is, it is moving towards your left. And the dinosaur is giving you the illusion that it is moving in the spot, which completes the illusion that the dinosaur is moving to the right. Now, what I'm trying to do here is using Python Arcade, I'm going to give you an illusion that the dinosaur is moving. So what first I need to do is to add some change x to the dinosaur, which would actually create a constant speed to the right. So imagine change x is 1, it will be a slow speed to the right. But if change x is say 2, you would notice that the dinosaur is now moved from its initial position to a different position. But remember, a dinosaur's actual position within the window should not change. Now, how to achieve that? Python Arcade actually helps you to move the camera. That's correct. You can see that the frame, the game window, seems to have shifted to the right, and the dinosaur's position relative to the window has remained the same. So the dinosaur might not actually seem like it is moving, but the camera is actually moving, and the dinosaur's x position would increase constantly throughout the game. So this is one thing to remember, that it's an infinite space. You will not actually run out of the x coordinate. The dinosaur would continue to run, its x coordinate would continue to increase, and the camera's x coordinate is also tracking the dinosaur closely. Now, in this step, we'd also draw the score on the top right. Unfortunately, if you do this, because the way the camera works, the x position of the score is not changing. So here, what would happen is that when the camera actually moves, the score would seem like it is shifting to the left. We will fix this. Ideally, we would want the score to remain at the same position on the top right position, static. But if you just have one camera, this is what would happen. Objects which are remaining at the same pixel position would appear to scroll to the left, which is what we need for certain objects like the ground. as you can see, if the ground does not move, it does not give the illusion that something is moving. So we want the ground to move, we want the background to move to the left, but the score should remain on the top right. So we'll do that in the next step. But for this step, we'll focus on how to make the dinosaur move and the camera move along with it. Now let's look at what code changes we need to make to achieve this. First, I'm going to set a constant which defines what the player speed is. I've noticed that change speed of 2 is actually quite good enough to give an illusion of similar speeds. I'm going to define what is called an arcade.camera. The camera would be the same width and height of the screen. Just to give you an idea of how long this line is just in our constructor, and camera sprites is nothing but a camera object which is stored inside self.camera underscore sprites. Next, I'm keeping track of the score. The score is actually quite easy to keep track of. It's quite similar to the elapsed time. In fact, the more time passes, the more you get scored. So it's indirectly keeping track of the time itself. Next, inside the update. So our update function was just changing the texture of the player. Now we are going to add a speed to the player sprite character, and that is set to the player speed. The camera sprite is, like I said, something that is tracking the player. So if the player moves, the camera also needs to move. You'll notice that the player underscore sprite dot left, which is the leftmost x coordinate, is used for the position of the camera sprite. It is slightly to the left. The camera is leaving a little bit of gap to the left of the player so that you can see the left of the dinosaur. And y position, y coordinate is set to 0. How do we calculate the score? The score is quite easy to calculate. Like I said, it is the position of the player, the left position, divided by 10. So this double slash indicates that it is a integer division, not a floating point. So we don't want to deal with dot some decimal value. We just want the integer result. So that will be our score, and scores are typically integers, so that makes sense. Next, you would notice that we are inside the draw function. I'm removing this comment which says that you would have artifacts if you don't use the filter. That seems to be a little bit of an workaround or some kind of a note about Python Arcade itself. So I'm just deleting that. Instead, I'm going to use the camera. So if you want to draw something and the camera position should be fixed for that, first you need to call self.camera.use. So here I'm calling camera underscore sprites.use before I do any kind of drawing, so that the drawing is done relative to that camera. And then you would notice that I'm drawing the scene and I'm drawing the score. Now, how do I draw text in Arcade? As it's self-explanatory, arcade.draw text. What is the text I need to draw? So the text I need to draw is a number, and I want to prefix it with 0. That is why self.score :05. So this is a typical string interpolation syntax. You can find this in the Python documentation. So this will prefix, say, a number like 10 with 3 zeros and 1 and followed by 0. So this will just give you zeros prefixing that number. Screen width -2 is where the x position is. Screen width height -10 is where the y position is. So this would give it a top right position. Arcade.color.black is the color of the text. 20 is the font size. Font name is Kenny High. Anchor x and anchor y is what these coordinates indicate, like what position the text needs to be at. Is it the top right? In this case, it is the top right. It could be middle or center or any of those positions that you would want to align the text to. So with that, we should be able to see a moving dinosaur and possibly an incorrectly moving score. Let's see that. Next, I'll show you how you can fix this score moving to the left, drifting to the left problem. Ideally, what we need to do is keep the score x coordinate moving. Uh, I'm sorry, that should not be said ideally. That's a workaround kind of thing. But ideally, what needs to be done in such games is we need to define a second camera where the score is painted, or any of the GUI elements in a game. For example, if you have mouse based controls or even a mini map, all those GUI elements of a game should be drawn using a separate camera. So that's what we are going to do in our implementation. You can see a new red rectangle which is similar to the game window, but it's always rooted at 0, 0. Inside this red rectangle, I'm going to draw this score. This is where our camera is going to be. And this once you shift to this camera, then the position of the score seems accurate, right? I mean, it's relative to the screen. So I'll use the first camera, that is to draw the dinosaur and all the game elements which are scrolling. And for drawing the static non-scrolling elements, I'll use this red outline. Let me show you how to do that in code. So first, inside the constructor, I'm going to create a separate camera. This camera is the same width, same height, but it's just a different instance for drawing GUI elements. Now I'm jumping to the draw function. Inside the draw function, you would notice that I'm going to use the camera sprite and draw the scene. The scene is practically everything that is scrolling. If you remember, our dinosaur is also a part of the scene. After I draw all that, just before I draw the score, I just need to call camera underscore GUI.use. Now that will ensure that when I draw the score, I'm using a different camera, so the scrolling does not happen there. Let's see how this works. So we have an amazingly animated dinosaur which is moving, but something seems to be missing, and that something is our ground. So the original dinosaur game actually calls the ground as horizon, because if you think about it, it's not really a ground. It is actually an illusion of a ground which is going disappearing or appearing somewhere in the background. So what you have drawn here, the thick lines over here are actually the ground, the lines which define the ground. And these rounded boxes are what we call as hitboxes. Now, what are hitboxes? Hitboxes are used to understand at what point the boundaries of colliding with this particular object should lie. So once we turn on physics, which we have not done so far, objects will start to collide. Objects will not be able to move beyond what they collide. What defines where they collide? That is the hitboxes. So there will be a hitbox which is surrounding the dinosaur. There will be a hitbox which is surrounding the ground. The dinosaur will not be able to cross the hitbox of the ground. So that is why I'm defining the hitboxes when I'm defining the ground itself. And you would notice that it is there are 4 pieces of the ground tile, uh, and there are 2 kinds of ground tiles. So in our assets, we just have 2 images which represent the ground. The one which is like a slight yellowish mustard color, and another one which is the brown color. So these, I'm going to use a combination of these two to give you the illusion that there is a lot of variety in the ground, whereas it's basically a random mix of 2 different tiles of the sprite. And one level is what I define as slightly longer than a screen. I think the screen is about 800 pixels wide, and I've defined the ground to be only 600 pixels wide. So to give you an illusion that it's much longer than the screen, I'm going to create a level which is made up of 4 pieces of the ground sprite. So that will be 6 into 4, 2400 pixels, which is plenty for you to scroll. Maybe at least at the minimum, it is 2 screens widths wide. So let's see the code to make this ground appear. Let's start by importing random because like I said, the ground is made up of two kinds of sprites shown at random. Now we are inside the setup function. Inside the setup function, just after you set up the scene, you can set up what is called a sprite list for the horizon. So why do we need a sprite list? Because we are going to have a number of sprites and it helps to keep it organized inside a sprite list. Now I'm going to look at for column range level width pixels divided by ground width. This should be 4 if you use the default values of the constants. The horizon type, which is basically which sprite to pick, should be a random choice. I'm going to pick either 1 or 2. This is why we need random. Next, I'm going to pick the sprite itself. So it is going to be directly picked up by specifying asset path slash horizon type, horizon hyphen horizon type, which is a randomly selected one. This is slightly different from using self.textures over here. Self.textures is kind of our lookup table or a dictionary. I could have used self.textures, but I didn't over here. Horizon underscore sprite dot hitbox is where I would define the size of the hitbox. This is basically a list which contains 4 elements or 4 coordinates. These coordinates are relative to the sprite. For example, the center of the sprite would be 0, 0. That's why I'm starting from my two negative values. The two negative values would start at the bottom left. So bottom left would start from negative 300 and negative 10. So that's kind of like lower bottom left. And then I would go up to 300, negative 10, 300, negative 6. So you would see that I'm working with negative y coordinates here because my actual horizon's hitbox should be a little lower than the horizon's actual hitbox. So by default, the hitbox is using the boundaries of an image, and I want the hitbox to be slightly shrunken, slightly lower, so that there is some space for the dinosaur to stand on. Next, I define the horizon.left, which is ground width into whichever column I would want it to appear. And finally, horizon sprite bottom, which is where the position of the horizon sprite should be. And I use all these coordinates to define the sprite, and I add that sprite to the sprite list. And finally, I add it to the scene, and I give it a name of horizon so that if I want to use any collisions, I have some name to define it by. And horizon.list is passed. Now, if you remember, we are drawing the scene in every time we refresh the screen, and all you have to do is add the sprite list to the scene so that it gets drawn. Anything which is drawn, a part of that scene would get drawn as well. So let's see how this looks like. Now, how would you give the illusion of an infinite horizon? Running out of the screen horizon is never happening in the real game. So it's quite easy. All you need to do is keep shuffling the ground sprites. So if there is a piece of sprite which is gone off the camera, which is scrolled off to the left, you can use that piece and move it to the front. So move it to the right and keep extending the ground dynamically. And that's what we're going to do, extend the horizon if the first horizon sprite goes off the camera. We are inside the on update function, and this is just after we calculate the score. So if we look at the horizon list first element and the rightmost coordinate of that, if that rightmost coordinate is less than the camera sprite's goal position, so this is nothing but the X position of the camera. What I'm trying to say here is the right of your sprite, the first sprite, is less than your camera's X position. That means the the ground has crawled off to the left. The ground is crawled off the camera to the left. It's not visible anymore. That means that the first element of this horizon list is now suitable to be used as uh, is suitable to be reused, right? You can move it to the end of the list and keep extending the horizon. So I'm going to create, I'm going to pop that horizon list first element by saying pop 0. I'm going to put it in this variable. I'm going to change the left coordinate of that, and I'm going to say self.horizon list last element -1 left plus ground width. So that is going to just extend from the last element to the ground width, and I'm going to append to that. So what I'm going to do here, essentially what I'm doing is I'm popping off the first element, I'm adding it as the last element in that list, and I'm adjusting the left position. This is all I have to do to give you the illusion that it's an infinite ground. The more you scroll, it does not stop. So let's see that. Let's try that.
$346 minutes later.
Fantastic. Now we have a scrolling ground and it does not seem to end at all. We can keep running forever and ever. Okay, we have an infinitely long horizon, but a lot of things seem to be missing. And that's why we are going to talk about how to add the obstacles over which the dinosaur has to jump. You know, the small cactuses, the large cactuses, and of course, our bird in the sky. The way I have designed this is to generate the entire level procedurally, even before it scrolls into the screen. So at some point before our entire level, so by level what I mean is the width of 4 platform tiles, that is 6,600 into 4, 2,400. It starts by looking at the smallest possible x coordinate value, that is now called x min, and gradually increasing it all the way till x max. So imagine that your screen is not yet, or your camera has not yet reached x min, and that is usually the point when the procedurally generated level is created. So how do we start? So we start from x min. We will roll some dice to determine, or a random number to determine whether we should show a cactus or whether we should show a bird. Now, when do we determine that a bird needs to be shown? A bird, if it is off the camera. Let me show you an example, another diagram. So have a look at this diagram. In this diagram, the bird has already been seen. The bird is off the camera. Now would be a good time to reuse this bird by just changing the position of this bird. Just check whether the bird is outside the camera. If it is, move the position of the bird to where the level is being created. This is how we are going to reuse the same sprite by moving the x coordinate and the y coordinate. Remember, the bird doesn't have a constant x coordinate. It could be anywhere up here, and the y coordinate is typically towards the end of the level. So a bird is kind of signifying that a level is getting completed. Now, how do we generate the cactuses? The cactuses are generated again. A random number is generated, and to figure out whether we need the big cactus or the small. I think it's a choice whether we need to have a big cactus or a small cactus, whether the position should be far or near. And once it is generated at the current exposition that we're looking at, the next exposition is a random distance away from the current cactus. So this way, cactuses have a gap that is randomly generated, and you will keep continuing this loop until the x coordinate reaches or crosses x max. So this is how we create an entire level procedurally. Let me take you through the code to actually create procedurally generated levels. The first thing I'm going to import is random integers. Random integers will be useful, as we will see later on, in how we determine whether a cactus needs to be shown or a bird needs to be shown. We need to import a few more textures to show the bird. Remember, the bird animation is also similar to the dinosaur animation, where there are two different frames to be shown for flapping the wings of the bird. The next bit of code might seem a little bit long and complex, but I'll take you through that step by step. Um, the first, as you can see, inside setup, just after the player setup, we are going to define the obstacles. What are the obstacles? As you know, the obstacles are the small and large cactuses and the bird, of course. So we need a separate sprite list for this. Eventually, we are going to create some sort of check uh, between whether the lists overlap. For instance, the player list and the obstacle list, if they touch, that means that the player has touched an obstacle, and this is a very quick way to find out whether a collision has happened and the game is over in this case. So we're creating a sprite list. Next, I'm going to create a sprite for the bird. In this case, I just have to create an initial image or a texture, as Arcade calls it. I could have used self.textures as I have mentioned here for players, but this is also a valid way. I'm going to call it, I'm going to set it to bird1 .png, but as we know, while drawing the bird, I need to make sure, just like the dinosaur legs needs to keep moving, the bird's wings need to keep flapping. So while drawing, I'll take care of rotating or flipping this image of the bird. Next line, I'm going to say the bottom of the bird is 100. This seems like a constant number, but this is just the initial value. When I'm going to recreate a level or when the bird moves off the camera, I'll give it a more dynamic positioning. Similarly, for the rightmost position of the bird is just at the end of the level, minus 100. So it's like 100 pixels before the level ends. And finally, I'm adding the bird to the obstacle list and adding the obstacles in a separate function called self.addObstacles. That is what I'm going to explain next. So it just takes three parameters: the self, the minimum x value, and the maximum x value. So I'm starting with a minimum x value of after 80% of the screen. So this is quite deliberate. I don't want any cactuses in the first 80% of the game, so that you don't start the game and immediately hit an cactus or an obstacle. I want the dinosaur to have a good 80% run, and then I want to start the obstacles to start appearing. The maximum x position is level underscore width underscore pixels. That is, as you know, about 2400 pixels wide. Next, I'm going to add the sprite list to the screen. So this ensures that I don't have to call the obstacle list dot draw when I'm drawing this. I just have to draw the scene, and since the scene automatically contains the sprite list, all the obstacles will be drawn as a part of that. Next, let's scroll to the add obstacles. I'm just going to scroll and make it the entire screen. This is a couple of lines of code, but I'll take you through this. It's nothing complicated. It's quite easy to understand. Essentially, what we're doing is, as I showed you in the diagram, I'm moving from x minimum to x max in this while loop, and going to add obstacles one by one. I'll start with a counter called x position, which starts with the initial value of x min. And then I'll check if the bird sprite is off the camera. So I'm just checking the rightmost position of the bird and seeing if it is below the camera's goal x position. If it is, I'll say the bird is off the camera. If not, it is I don't need to recreate the bird. And then I'm going to keep incrementing xpos. Xpos increment happens somewhere over here. And I'm going to keep incrementing xpos until it is exceeding xmax. Then I'll generate a random integer between 1 to 5. And if it is 1, and if the bird is off the camera, I move the bird's bottom to the position mentioned over here between 40 and 80. The left position, that is the x position, will be the current x position, and the x position will be incremented by the bird's width and a random integer. However, if the random integer is not 1, which happens about 1 in 5 times, getting 1 out of 5 is about a 20% chance. If that 20% chance does not happen, then we are going to create cactuses. So like I said, the size of the cactus is a random choice. The variant of the cactus, remember there are different shaped variants of the cactus, just to give you a variety in displaying the landscape. It could be type 1, 2, or 3. And there are large and small variations for this. So once you determine that, I'm going to create the obstacle sprite. The obstacle sprite is created directly from the file position cactus size variant. This naming convention is followed for our image files, so it's very easy to pick up. Then the obstacle sprite's left position is the x position. The obstacle sprite's bottom is taken as 20 if it is large, or 24 if it is small. So the size of the cactus matters in determining where the cactus is positioned. It is not a perfect science, so if it is large, we need to make some small adjustments to the y position of the cactus. And then finally, we are going to create a random gap, or an inter-cactus distance is generated randomly. The sprite's width is the minimum, and a random number between 200 and 400 is picked up, and another width is added to it. So totally we have a lot of gap between the cactuses. And finally, the obstacle list gets added with this obstacle sprite. So the obstacle list keeps growing. Eventually, I think we'll run out of memory, but in this case, it's not a big issue because we are talking about a very small number of cactuses. But I guess there should be some mechanism where we, just like we do for the bird, we pop out the cactuses which are no longer in display if you want to really conserve memory or reuse memory wisely. Next, of course, we need to make sure that the bird animation works. So similar to what we did for the dinosaur, I'm going to divide the offset by 2 and then perform a division reminder by 2. This is to make sure that the bird is not flapping as fast as the dinosaur. If you remember, the dinosaur is running very fast, but the bird flapping is a little slow. So this division by 2 is done for that. And then of course I have to add it by 1 so that 0 or 1 is mapped to 1 or 2. And then the bird sprite texture is changed by using self.textures, our dictionary, and calling bird-bird frame. So with these lines of code, let's see how the results look like. Oh, look at that. You have a bird now. You'll notice that the level does not continue to generate obstacles after the initial set of obstacles are created. This is easy to fix because we have an add obstacles function. We can keep calling that when the new level is being generated. Let's do that. So Next, I'm going to check whether the bird or the cactus hits the dinosaur. Essentially, I would need to create a physics engine in the parlance of arcade and figure out whether the bird, the dinosaur or the player list is colliding with the obstacle list. I don't want to end the game. I just want to show a message printed on the console like it has been hit or it has not been hit. So for that, I'm just going to create a debug mode where if the debug mode is turned on, the game is not going to end and it's going to continue, but it's just going to say that print that an obstacle has been hit. For this, I need to create a new constant. I'm going to call it debug. It's a very standard naming convention, and I'm going to set it to true. Next, I'm going to go to setup. So we are inside setup here, as you can see, and within setup, I'm going to create what is called a physics engine in arcade. So arcade physics engines are quite interesting because we have a number of them, but I'm going to use a simple physics engine called the physics engine platformer. Physics engine platformers could be used for creating platform games. Platform games are similar to games like Mario, where a character can jump from a level to a flat surface to another surface, maybe higher or lower, through jumps. So you have to define the gravity. I'm going to define the gravity to be 0.4. Should have probably defined this as a constant, but it's okay. I also need to define what is a player and what is the surface on which the player is standing on. So I'm going to pass the horizon list because if the player is standing on the platform, it needs to stop jumping, and the whole jump physics is handled here, making the whole job of making this game quite easier using Python Arcade. So that's the physics engine that we define here. An important part of creating a physics engine is to keep updating it. So inside my update function, I'm going to call the physics engine update. After that, I'm going to check for collisions. So the collision check code is quite simple. I'm going to call this player sprite, whether it collides with the list, which is the obstacle list. Remember, our obstacle list includes both the cactus and the bird. So if it is colliding, then there should be a non-zero length list inside this variable called collisions. So that's what I'm checking here. If the length of the collision is more than 1, and if the debug mode is set to on, print a hit. So that will tell you that something has been hit. The game does not end. It will just display the hit. Most probably it'll display the hit a number of times for just one collision. That is because the player needs some time to move away from the collision, and the whole time the collision keeps showing as hit. Next bit of code is again inside update. I'm going to add more obstacles when I extend the horizon. You must have noticed in our previous run that the obstacles were only generated in the first part of the level, in the initial part of the level. After that, the horizon keeps extending, but the obstacles were not added. So I'm going to add the obstacle starting from the rightmost position of the ending horizon list, right? The last part of the horizon list. And then I'm going to extend it until the rightmost position of the horizon list. So since we are extending the horizon one tile at a time, I'm going to add the obstacles also one tile at a time. So this makes it quite dynamic. This reduces the overhead or the jump you experience when the level is being procedurally generated. You might have noticed this in actual games which you can buy, where a player is going to enter into a new territory, and there is quite a visible or quite a known delay or a lag before that level gets generated. So generation of a level should be timed in a way that it does not take a very long time, so that the players do not experience that jarring lag when they are going into a new part of the level. Next is an important part of debugging, which is to draw the hitboxes. So Arcade provides this ability to draw the outlines of the hitboxes by just calling dot draw hitboxes. You can in fact define what color you need, and I have taken some effort to define them in different colors. The player would be defined in a green variant called Bangladesh green. The obstacles, the cactus and the birds, would be shown in a red called barn red, and the horizon would have an outline using Catalina blue. Why am I drawing the hitboxes? Because since I'm checking collision here, I found there are so many bugs which were um, because of the way I wrote the code initially, which were not clear why the hits were happening. So once I made the hitboxes visible, I was able to see where it was being hit and if the hitboxes need to be adjusted. So right now it just remains as an artifact of that process, but I would highly recommend you to keep these lines in the code for the future debugging purposes. Then let's see how this code looks like. So now we have an infinite scrolling terrain as well as infinitely generated obstacles. It's quite funny to see the hitboxes in various shapes. You might expect hitboxes to be rectangular in shape, but actually the hitbox is much more closely wrapped to the outline of the shape of the object. So I would call them hit polygons because they are different shaped polygons, and the dinosaur one is actually quite interesting because it has that flat bottom and it's almost like a moving rock or a sliding rock moving over the surface. You can see it every time there is a hit, it appears on our console, and this is quite useful to see that the whole collision algorithm works. So once we add the jump capability, this would be even more effective to see that, you know, where it hit. Instead of just ending the game, it'll be much more useful in fine tuning your collision. So far our game is doing well. We have created the obstacles and an infinite scrolling terrain, but our dinosaur isn't doing much. It seems like our dinosaur needs some sort of actions, like it should have the ability to jump, duck, and respond to different situations. For that, what typically happens in a real actual production quality game is a player is given different states. So let's try to emulate that. I'm going to give our dinosaur different states. In fact, I'm also going to give our game different states. For example, the game is running as well as the game has ended. However, for the dinosaur, we need a lot more different states. When the game starts, I'm going to give the dinosaur a state of idling. This is when the dinosaur is waiting for the player to press a key, and once you press a key, the game starts and the dinosaur starts running. This is quite noticeable in the actual Chrome browser. Whenever your internet is down, there will be a dinosaur blinking at you and waiting for you to click the mouse or, you know, touch its sprite character so that the screen expands and becomes the actual game. In our case, we would define a state called idling, but in most cases the game would just start by the dinosaur being in the running state. Now there are two different states over here in addition to running, called ducking and jumping. So ducking is when the dinosaur is bending its head when an obstacle comes overhead and it wants to look shorter. And jumping is when, of course, when it wants to leap on top of the cactuses or jump over the cactuses. The arrows indicate from what are the possible states from a state you can jump to or transition to. While running, you can move into ducking. While running, you could also move into jumping. In fact, all combinations are possible as well, because when you're jumping, you might suddenly want to go into ducking, etc. Uh, One thing to keep in mind is sometimes these states are should not be taken too literally. For example, when you're running and you're ducking, you're actually running while you're ducking, right? So ducking does not exclude the fact that it is still running. The dinosaur is practically almost always running. There is no rest, there is no stopping for the dinosaur. It's constantly running. So this is just to explain different states of the dinosaur. Uh, the concept of states helps you much better than the concept of using Boolean switches like is running or is ducking, because at any given point, dinosaur could be only in one of these states, and it massively helps in much more complex games to have states rather than individual variables. And finally, we have the state called crashing. This could happen in any of these three states, that it hits an obstacle. That collision will let you transition into crashing. Once you're in crashing, we would set the game state also to end, and this is how we know that the game is over. So this is the what we call a state transition diagram. So let's start with a few imports. I'm going to use a Python relatively new capability called enumerators. Enumerators are nothing but different names given to integer values that a variable can take. This is quite useful in representing state, as we'll see shortly. And the exit. So exit is needed if when you collide with something and you want to end the game, right? So I'm going to import exit from system. We would need to represent different states of the dinosaur, especially when it is ducking or it's being crashed. So I'm going to import those textures here. Few more additional ones to represent the different states of the dinosaur. This is the most key line in this part of the code. I'm going to create an enumerator. So an enumeration of the states, the first parameter that you'll have to pass is what do you call the class which represents this enumerator. I'm going to call it Dino states. And then I'm going to specify what are the states separated by spaces. So the states are idling, running, jumping, ducking, and crashing. And I'm going to create another enumerator for representing the states of the game states. So the game states are either it's in a playing state or it's game over. Once the dinosaur crashes, I'll ensure that the game state is changed to game over, so that you're not playing anymore. Now I'm going to give an initial state of idling for the dino state, and that's how the game starts inside the constructor. Next, I'm inside setup. So setup is a good place where I want to set an initial value for the game state, and the game state is set to an initial value of playing. So this is not set in the constructor, because every time I call the setup is when I'm initializing the game, and every time the game is constructed is when that constructor state needs to be set. Continuing in setup, I'm still inside setup. I'm going to create the dino state as running. So once the game starts, that will be a good place where the dinosaur state can be set to running. Next, I'm going to add two new methods, right? So arcade helps you to define or handle keys by defining these two functions called press and release. So on key press is when the key is pressed down, and on key release is when you leave the key. So when your finger is on the button or on the keyboard key, it'll call keyboard press, on key press, and when you when your finger leaves the key, it's called on key release. You can compare the key which is passed with different predefined values given in arcade.key. So when you press key, that is our jump key, right? For the dinosaur to jump. I'm just going to set the dinosaur state to jumping. I'm going to set the physics engine to jump about 6 pixels. So this is how I define how much it has to jump. Why 6? 6 comes from various trial and error values. I find that 6 to be a little too high than the usual dinosaur jump you see in Chrome, but it makes it more fun also and a little more easier to play. I'm also going to define another key to exit the game. So far we don't have anything, so I'm going to say key. If you press the escape key, the game will exit, or the program itself will exit, and that's why I'm defining it here. Now remember, once you leave your finger off the space key, the dinosaur needs to stop jumping. So that's why the dinosaur state is set to running. And the hitbox needs to be also defined to be the hitbox of the dinosaur running. This is to make sure that if it's in a different state, like say for example ducking, the hitbox is a little different for ducking. You'll see that very soon. So let's see how this code works. I'm really bad at this. I should stop hitting onto obstacles. Okay, I think I'm getting the hang of this game. Notice that it has a multiple jump capability. I did not prevent this from arcade, but arcade helps you to jump on a jump. Jumping while you're jumping is not possible in the original Chrome game, but this is very helpful for me to debug. You can literally be flying in the air. I mean, of course, there is a way to prevent jump on the jump in Python Arcade, but I'll leave that as an exercise for you to figure out by reading the arcade documentation. I find this to be more fun, so let's keep that. Next, we're going to implement ducking. Ducking is when the player itself looks like a smaller version of the original player. So the hitboxes and all those changes needs to be kept in mind. So let's see how we do that. First of all, let's change our key press on key press function. We need to define a new key, which is the down key, the down arrow key. When you press the down arrow key, you need to change the state of the dinosaur to dinosaur states ducking. And most importantly, we need to change the hitbox to look like a ducking hitbox. So once that hitbox is changed, now the collision of the dinosaur will be calculated slightly differently using smaller boxes, and it will not hit objects which are on a slightly higher y coordinate. And this is what we want. We want to avoid hitting objects when we are ducking. And we need some changes on key release also. So if we are releasing the space key, the dinosaur continues to run. We need a similar capability for the down key as well. When you release the down key, the dinosaur needs to change from the ducking state back to running state. So that's what it does here. It checks whether it's whether you're releasing the down key, and it continues to the running state. Another check that needs to be done here is whether the sprite is positioned correctly. What I noticed is that when the positioning of the sprite is changed for ducking, and you come back to running, the running of the dinosaur resumes at a slightly different y-axis, at a slightly different y coordinate, which makes it look off. So I want to make sure that the center y is corrected when you're coming back to this running state. Next, I'm going to change the animation slightly. For example, earlier, if you look here, the sprite was based on whatever running state was happening here. So if you look at the red region here, it was just switching between the running states. So if you're in the ducking state, I want to change the animation slightly. want to use the textures which are either Dino hyphen duck hyphen 1 or 2 instead of run hyphen 1 or 2. So that just changes the animation to make sure that the ducking state is also animated correctly. And that's pretty much it. Let's see how this code looks. The ducking works perfectly. In fact, you can jump and duck at the same time. Excellent. Now I think we have done a fantastic job in creating the collisions and identifying when the hit happens. So it's about time that we turned off the debugging. So that's what we are going to do next. We are going to turn off the debugging and we are going to make the collisions matter when the game, when you hit something, the game should end. So I'm going to turn off debugging by setting it to false. Next, inside the key release, I'm going to check whether the game state is over. Why am I doing this in key release? Because this is probably a occasional thing. So, whenever there is a hit, it'll probably notice over here. You can do this anywhere practically, so it doesn't really matter. Next is inside update. One of the first things I'll check is whether the game is over. If the game is over, I want to show something like the dinosaur is in a crash state. So that is what I'm going to do here. The dinosaur needs to stop running. So that's what the player sprite.changex is 0. And I'm going to return from update. I don't want to do any of the remaining calculations. Next is I'm going to remove that print statement which I used to use over here. Instead, I'm going to change the logic to if there is a collision and if the game is not in debug, then let's change the dinosaur to be in a crashing state and the game state to be a game over state. So this is essentially stopping the game. This is essentially telling that let's be in a pause, let's keep the game state over and the dinosaur state in crashing. And finally, we need to show a game over message. So here we are inside on draw and I'm inside the GUI camera section of the code. So this is where I draw this score. And after I draw the score, I'll just make a check if the game is over. And if the game is over, I need to show the game over in the middle of the screen. That's why I say screen width divided by 2. And I need to show it somewhere on the top. So it's like screen height minus 30, about 30 pixels below the top of the screen. It should be in black color, 24 point size font in the same standard font. And it should be on center and on top. So this would give that game over message at the end of the game. So that's all the code is. Let's see how this code works. The game over works perfectly. So it might seem that everything is working fine. The implementation of the game is practically over, but it's all in the small details that matter, right? And we do not have a background of moving clouds, which gives you the impression that something is there in the distance, something that is moving. This is called a parallax effect, and we'll implement parallax effect next for the clouds. So we need to define a couple of constants here. At the top of the game, I'm going to define that there will be 3 clouds which are visible at any given point in time. The logic for the clouds would be similar to that of the birds. When the clouds move off screen or off camera, the cloud needs to be moved back to where it's going to appear next to the right. So it'll be shifted from left to right when it moves off the camera. I also need to define the minimum position of the cloud here. So the minimum position of the cloud means what is the range or y position range for the clouds to appear. So I would want it to be between 100 pixels and 140 pixels. And the speed of the cloud should be a very slow speed, and it should move in the opposite direction of the dinosaur. If the dinosaur is moving, running to the right, the cloud should be slowly drifting to the left. That's why the cloud speed is negative and it's 0.5. Next, I'm inside setup. So let me make this a little more wider so that you can see better. So you can see that inside setup, just after we create the scene, I'm going to create the clouds. you would notice that I'm following the order from whatever appears furthest in the scene to whatever appears closest to the scene. So it's quite important that you add the clouds in the beginning so that it appears behind everything else. Now I set up a sprite list for the clouds, which is quite standard. We have done that number of times so far. That's what's happening here. Then I'm going to create a loop. We are having 3 clouds, so this loop will run 3 times. I'm going to create a cloud sprite, which is from one of these assets called cloud.png. I'm going to define its left in a random location somewhere in the width, along the width of the screen, and the top position is somewhere along the between cloud y position minimum and y maximum. We have defined these two constants, and I'm going to add this to our sprite list. So I'm going to add create each cloud sprite, and I'm going to add it to the list. And whenever this cloud moves off camera, like I said, I'm going to shift its position to the right. So that's happening inside on update. So each time there is an update, you can see I'm going all the way till the end to check whether I should shift the clouds for parallax effect and spawn new ones. So in this cloud list, I can move all the elements inside the cloud by a particular speed. So one thing I could have done is I could define the change X of the cloud. That would have made it much more easier. I didn't have to do this. But then this is another way to do manually set the position of every Y coordinate. In fact, in this case, it's the X coordinate of the cloud. Both ways are correct. Here I'm I'm shifting it by cloud speed X coordinate, and I'm not giving a Y coordinate. So it's going to just drift to the left. For every cloud and cloud list, if the right position is less than 0, that is if it is going behind the camera. Notice I'm not having to check the camera position over here, because here the camera is not the sprite camera, it is the GUI camera. So the GUI camera is not a moving camera, it is always at 0 position of your screen. So I know that if it goes below 0, it is off that particular camera. And the right position of this cloud is now shifted to screen width and to a random position, which is 25% more than the screen width. The top of the camera of the cloud is again randomly determined from one of these cloud positions. Next, where do these clouds appear, or more importantly, which camera do they use? So that I'm defining inside draw. You can see that I'm going to use the GUI camera once again before the actual GUI camera usage was over here. Before I'm going to use the sprite because like I said, when I'm drawing, I need to draw from behind to forward. So first I need to use the GUI camera, which is a stationary camera. I need to draw the cloud list using the same filter GL nearest so that the same pixelated look appears. And then I need to use the sprite camera to draw the sprites. And again, for the second time, I'm going to use the GUI camera to draw the score, to draw the game over state, etc. So this might seem like a little inelegant solution, but essentially I need to use the GUI camera twice. I think that's pretty much it. Let's see how this code runs. And that's it. That's pretty much how this dinosaur game is going to work. Happy playing. Before we continue, a quick note on how these images were made. Drawing them myself would have been a huge mistake. So I simply reused the original Dino game assets from the Chrome GitHub repository. However, they were all in one image, probably to reduce the size and image fetch requests. I used the GIMP image editor to cut out each image as closely as possible, then save them as separate PNG images in the assets directory. Don't like the scenery? Bored by the clone army of cactuses?
Or is it called cacti? Or is it both? Oh wow, yay! Open up the cactus image in an image editor. Draw the first thing that comes to your mind. A T-Rex eating creeper? Why not? Let's up the stakes with a falling meteor. Add two images of an animated blazing meteor. Now use the same technique as the bird. Give the meteor an initial position towards the end of the level. Make it move diagonally until it hits the ground. Does it hit the ground? Recycle the same meteor by resetting its position so that we'll meet it again. Prehistoric worlds might have been deadly, but there should have been nice things to pick up, like food. Create a chicken leg image. Again, the same approach to reusing it. If the dino touches the food, then move it further. Ideally, you can increase the score, but since it is locked to the distance traveled, this could recharge, say, your health meter. Results. Here is something interesting. If you compare the lines of code, our Python version is much smaller than the JavaScript version in Chrome. Of course, we are leveraging the Python arcade library, so it's not a fair comparison, but it shows how much help the library helps you in making a game from scratch. If you're interested in a proper game programming course from me, check out the link in the video description below. Here's a cool backstory about this game. Why dinosaurs? Because they have been around forever. But seriously, it makes a lot more sense if you think about it, when this game should appear. It is when you're not connected to the internet. The creators of the game thought that this should remind you of a prehistoric time when dinosaurs ruled. So, to make it fun, they made a runner game with a T-Rex in a monochrome setting. The visual style is a nod to Google Themes' tradition of the pixel art style in Chrome's error illustrations. If you like what you saw, please don't forget to like, share and subscribe so that you see more content of this kind.